In this video, I want to take a look at the notions of rank and nullity. These are two numbers that are associated with a matrix. First, a theorem. The row space and the column space of a given matrix have the same dimension. Now, if you think about how we found the basis of the row space and how we found the basis of a column space, is we took the matrix and we put it into reduced row echelon form, and we looked at, for the row space, we looked at the rows that had leading ones to get us a basis, and for the column space, we looked at the columns that had leading ones. Well, of course, there's the same number of leading ones, whether you're thinking of how many rows have leading ones or how many columns have leading ones, because each column or row has only one, has at most one leading one. And so the number of elements in the basis for the row space would have to be the same as the number of elements in the basis of the column space, because they're the same number of leading ones. Okay, so this allows us to make this first definition that says, given a matrix A, we define the rank of A to be the dimension of the row space. We could have also said the dimension of the column space. Some textbooks say the joint dimension of the row and column space, right? The rank, the dimension of either the row space or the column space. Then there's the notion of the nullity, and the nullity of a matrix A is the dimension of the null space. Remember, the null space is a vector space, and the nullity is the dimension of that vector space. The row space, the column space, these are vector spaces, subspaces of Rn or Rm, right? And the rank is the dimension, how many elements are in the basis. As an example, I'm going to use that same matrix I've used for the last couple of videos here, with the 6 in here as it's supposed to be. If I take a look at this and I put it in reduced row echelon form, I can see that there are two leading ones. And the leading ones tell me that the rank is 2. Now, you may also recall from the video where I was finding a basis for the row space and the null space, and that to find the basis for the null space, we had an extra column of, well, we had an extra column of zeros here for the augmented matrix for that homogeneous system, which then just stuck an extra column of zeros on this end. But the point is, these first 5 columns are the same as they are here. So the nature of the solution space for the homogeneous system, so the null space, has really nothing to do with the zeros over here. It has everything to do with how many free variables you have here. And the free variables correspond to columns that don't have leading ones. Right? And so I can see, and we did see in the previous video, that there are 3 columns without leading ones, which meant we put 3 parameters, R, S, and T, in there, and then we ended up with 3 vectors as our basis for the null space. So the nullity of this matrix is 3. The theorem here. This is actually several theorems in the book combined, just to get a bunch of things all organized in the same place. If A is an m by n matrix, then the claim is the rank of A plus the nullity of A will always be n. That's the number of columns in this matrix. Well, you can see what we did up here. The columns with leading ones give you basis elements of the column space or the row space. And the columns without leading ones lead to elements in the basis of the null space. So the number of vectors that we either went into a basis for the row space or a basis for the null space was 1 for each column. And so the number of columns is n. The rank plus the nullity is n. We've already talked about this here, that the rank is the number of leading ones in the reduced row echelon form, and the nullity is, of course, the number of columns without leading ones. We would say it's the number of free variables in the solution set of the homogeneous system. Right? Another thing is that the rank of A and the rank of A transpose are the same. Well, it's not like you just take the transpose of this matrix and then put it in a reduced row echelon form. I don't get the transpose of that, right? I get something else. But the thing is, this right here shows that there are 2 independent columns. It also shows 2 independent rows, is what I meant to say. There's 2 independent rows. So when you take the transpose, those rows become columns, and so you're going to have 2 independent columns once you get to transpose. So there'll still only be two leading ones, right? Or however many independent rows you have here, they'll turn into independent columns when you take the transpose, and there'll be that many leading ones. Okay. And so the rank will be the same. I mean, in a sense, you can say that too, is because the column space of A is the row space of A transpose and vice versa, right? Because the rows just turn into columns. So the rank should be the same. And then we can say that the rank of A plus the nullity of A transpose should be M, where M is the number of rows in your matrix, right? I think this might look cleaner if it said rank of A transpose plus the rank of rank of A transpose plus the nullity of A transpose is M. That would be very much like that first one here, talking about columns, where this one would essentially be talking about rows. Well, it's talking about columns of the transpose, which would be rows of the original matrix. Okay. But because of number 4 here, you could say either rank of A or rank of A transpose here, and they're the same number, so that would be just fine. And lastly here for this video, this is a theorem that we've seen a couple times before, but again, just new terminology allows us to say it in a different way. It says, if ax equals b is a consistent linear system of m equations and n variables, and if the rank of a equals r, then the general solution contains n minus r parameters. Okay. Remember, we've seen this before, that when you can describe the solution set of a non-homogeneous system by finding one solution and then adding on all of the things from the solution set of the homogeneous system. But what we know about the solution set of the homogeneous system is it's the null space, right? And the null space has dimension n minus r. So when you start adding on things from the null space, you're adding on things that are linear combinations of n minus r things. That n minus r comes from here. The nullity is n minus the rank, and we said the rank is r. So when you take that linear combination of the basis for the null space, there's n minus r things, and so each one gets multiplied by a constant and then added up. Those constants are the parameters describing the solution set here. Okay. So we've seen this before. It's just that now we can state specifically that the number of free variables, the number of parameters, is going to be the number of columns minus the rank. So anyway, there is the concept of nullity and rank, and just a few theorems relating them.